Hello everyone. Today let's discuss about mean square error gradient. This is high definition picture, so you can go and look for the size settings of the high definition. Okay, coming back to our demo, what is mean square error? Mean square error is the distance from the data points to the actual model, and we calculate the distance by squaring them and sum all of the difference together, and we calculate mean square error. So with the help of mean square error, we try to see whether the given model is accurately is coming or not. So this is one method of you doing the model prediction. So let me go into the demo. So here I have loaded the libraries along with California housing. Now here you can see I'm getting the house data. So in the house data I have 9 different parameters. So in these 9 different parameters, target is something is related to house pricing. So here what we are doing is we are taking the features and then we taking the targets from the housing data, and then we are joining them as a data frame, and we finding out the correlationship. The correlationship is something that what is the impression of one dimension on the other dimension. If you see the income indicator here and housing age here, the value is negative. It means that when income increases, house age decreases. When house age is increases, the income decreases. So this is inversely proportionate. If you see here, the income with respect to average number of rooms, it is the positive value. And so the more the value, it means more the change. Since it is positive value, it means when income grows, the average number of rooms will grows, or if the average number of rooms grows, it means income will grow. So these two are proportionate. So like this, we can understand the relationship of one dimension onto the other dimension. If you see here, I took two dimension. One is income and house price, and run this describe. So in this, what happening is, so you can see what the distribution, you can see the distribution of these two dimensions, and you can check the spread over all the dimensions. So if you want to improve the dimensions, what you can do is you can filter out some of the values basing on a particular threshold value, and when you run on the describe, you can see the smooth distribution among the two dimensions. Now here we look into this normalization. So what is normalization? So given when you have dimension, for example, your car gives 10 kilometers mileage, it means it will take 1 liter for 10 kilometers mileage. What if you want to change liters to milliliters and say 1000 milliliters for the mileage is 10 kilometers? What if you want to change kilometers into centimeters? Then it means 1000 milliliters for 10,000 kilometers. So these values are large because of the matrix change. So in order to reduce this ambiguity, we use normalization. So in this normalization, what we'll do is we'll take for a given dimension, we take the maximum value and separate with the minimum value and find out a proper proportionate value so that it fits between the range of 0 and 1. If you see here, the after normalization, the x value, the maximum value of x is 1 and maximum value of y is 1. Now we will plot the graph between house price, that is the target, and income, that is made income. So we can see the spread of the data points. Now what we can do is we can have a simple linear regression. We can use the closure formula. So here we can calculate x mean with xy, and then we separate with the xy mean and divide with the mean of squares, so that we'll get the slope and bias while calculating for all data points. And here, once we get the slope and bias, you can predict for any given input, you can predict what will be the house price, and then r square. So r square, what we do is we'll check the difference between the predicted and the original mean, and we'll do sum of squares, and then we'll return in this particular formula so that we can calculate the mean square error rate. So here is the function to plot the graph, and here we are taking these two dimensions as income as x and house price as y, and we are performing the linear simple regression, which is a closed form solution. So here when we fit and then we start predicting, we call this plot regression, and then here we draw a graph. But here you see we will getting mean square error. So mean square error, so you can download from the library, from skill learn metrics. So when you give the predicted value and the actual output, it will calculate what is the mean square error. So with this you can identify what is the uh, what which is the best model that fits the data. Now here what we did in this graph is we are using two graphs, so it's easy to plot. But since this is about 8 dimensions, it is not easy to plot a graph. So instead of how we can verify this algorithm is with the help of mean square error. With the help of this mean square error, you can check whether the model is the best fit or overfit or underfit. Now, this is the closed form solution. You can see we are using inverse. We are calling inverse of x3 dot and x3 dot. So this is a kind of closed form. Sometimes it will take a lot of memory and it may even go for crash. So instead we can use something called gradient descent algorithm. So in gradient descent algorithm, what we'll do is we initialize slope and bias, and after initializing, we will start predicting the values, and we will update the slope and bias with the derivative of the function. So when we are updating with the derivative of the function, we will reach to the proper model that fits the data. Now here we have a graph. Now with the help of gradient descent algorithm, we have this model. If you see this mean square error, this is almost same as the closed form solution. This is the 2D closed form, and this is from the gradient descent. The mean square error is almost same. So here the performance has been improved, so we don't have to worry for large set of dimensions and other increments. Now if you see here, in the code, we are iterating through the for loops. So it's epoch is nothing but the number of iterations that we are running. So here we have given 100 iteration, but even if you give 100 iteration and stepping up the model slope and bias, you can see after 20 iterations, it seems like meaningless. So you can, instead of having 100 epochs, you can have 20 epochs and you can get the best model fit. Now we have another algorithm called stochastic gradient descent. This is another popular algorithm. So if you see, you look into the gradient descent, you see we are using all the rows of the x. You can see here we are considering all the rows of x. So that's why the performance is little bit lesser here. In stochastic gradient descent, what we do is we'll take the random data space, and then we calculate the prediction and we update model accordingly, so that it will take less time to calculate these things and we'll get accurate model. Now we see when we run this stochastic gradient descent and then we plotted the graph, we see we got the accurate model which gives this mean square error. It's and if you see the how the mean square error rate changes with respect to the iterations is quite fluctuating, because we are randomly picking up the data points and then calculating it. So this fluctuation may not be smooth, but performance good and accuracy is also good. So if you want to compare with gradient descent and the stochastic gradient descent, so we can have x and y matrices, and then we will run this stochastic gradient descent and then gradient descent considering the time. If you see the difference is the stochastic gradient descent is 36.2 millisecond, whereas descent is 175 millisecond. So with this we can conclude mean square error gradient descent. So I hope you enjoyed my video. Now look into the description. I will mention the pages of the uh, uh, pages of the particular topic that I am covering, along with the videos and the code here, so that it is easy for you to watch the code and refer the code at the same time without changing the window screen. And also I have given certain references for you to refer. Thank you for watching my video. If you are not subscribed my channel, please subscribe it. For any comments or likes, please let me know. Thank you very much.